So, yes, where are we? So this is what happens now. I'll give you a little tour. Okay. So when we do the region inference, actually wrong directory. If we go into the NLL module, there's this kind of flow here where we start out creating the region inference context. And then we actually, this is in the context of the larger borrow check, I guess. Let's start with that. We come into do mirror borrow check. And the first thing we do, we rewrite the mirror to have variables. We gather up some move data, apparently. Actually, this step is already kind of interesting. So this replace regions in mirror. Where is it? Am I in the middle directly? Okay, that's here. And you see it computes the set of like named lifetimes declared on the function, does some renumbering. Okay, nothing too exciting. Then we do a bunch of other random stuff that I don't care about right now. And we call compute regions, right? And here, this is where we do this. This is where things are going to get a little interesting. So we compute the liveness of local variables. We figure out which variables are live where. Might be used later, right? And then we do this type checking. And what that does is produce, if we go to the type check, it produces some information. And in particular, it produces this liveness set, which is the set of all regions and locations where they're live, right? And it's super inefficient, and that's what's causing us the problem, by and large. Interestingly, Polonius uses more or less the same representation, so you know, but you don't have to worry about that now. We'll come back to that. It's a different problem. So then this is where I wanted to talk about. So after we've done the type check, doing the type check creates a bunch of region inference variables, right, in the course of doing its work. And right now, oops, if we look at the type check, it does some stuff, but right here is where it figures out what is live and where. So it's kind of in the middle of doing other type check related things. I don't actually remember how this works. It passes some closure to this function, and I guess this function invokes that closure right at the end for X. This is the reason it's set up this way, is that the type check gets used even when NLL is turned off as a kind of sanity check. And so this sort of closure is like extra NLL specific stuff. And so we could move this to the end pretty easily, but and now it's the last thing. Anyway, I'll come back to that. So we do this type check. We figure out how many, and in the process we create region variables, and we're doing that all in this inference context, which is this stuff from the old school region checker that we're kind of leveraging here. And so what this take region var origins does is at this point, when I call this function, we have to be done making variables, no more variables after this point. And so it takes all of their, the origin information, like why they were created for each variable, and it leaves behind some none value or something. So if you try to make a new variable after this, it'll panic. And that's a nice invariant. Now we know how many variables there are. We can like size tables, and just in general, it's good to know when you stop accumulating new data, right? And so then we call this region inference context new, and that's where we create the region inference context here. And we give it, for example, this var infos. This is the set of variables that was created. And we also give it the stuff that type check told us, like, well, we give it the outlives constraints anyway. And so what happens now, this is the thing I wanted to show you specifically, is right here, now that we know how many variables there are and stuff, we make this bit set that is the set of liveness constraints, which is basically for every region variable there's a bit set, and it has one bit for every point that is either true or either in the bit set or not in the bit set, right? And it's still an O(n) squared representation, but it's significantly more compact than this giant vector. It's also not one big allocation. So actually, when I first wrote the code, it was one big allocation. So I had a dense bit matrix, is to say, you know how a bit set works, right? A bunch of integers.
Oh, yeah.
Yeah. And so I basically had all of the bit sets for the variables end to end, and then you would select like a slice of that big array to get the one for a specific variable. But now that was kind of wasteful. It's efficient in some sense, but very wasteful. And so now we are doing sparse bit matrix, and that's actually good. That's to our advantage here, because to do the big vector trick, you have to know the size ahead of time. To do a sparse thing, you don't. But so this is exactly the region values new is what I was thinking we could move earlier if we refactor things not too much so that it doesn't expect to know the number of variables before it starts.
Sure.
And there's a second argument, though, you may have noticed, elements, which is created up here. That takes, I'll explain what that is it's a map that translates for each possible value. Basically, regions in the NLL consist of sets of points and also sets of the free lifetimes, like tick A or tick B, that are named. So you can have kind of combinations of those. And so what elements does is it's just a map from each of those possible things that can be in a region to an index. I'll show you. So it computes, for example, it computes the number of statements before every basic block and stuff like that, so that it can very quickly say, given a location, what is the index that corresponds to it, right? And like, where's the code for that? Like here. So when we want, hold on one second. Okay, so yeah, so that's all that does. And in particular, it doesn't need to know how many variables there are. It does need to know how many universal regions there are, how many named lifetimes. But we know that. So if we go back to back here, we actually compute that way up in the renumbering stage. So we know all that information, so there's no reason we couldn't move this thing to happen anywhere before type check. And then we could create the region values. Here we just have to kind of refactor sparse bit matrix so that it doesn't, I think it just doesn't need to know how many region variables there are, actually, at all. Instead, I would probably, I think my ideal would be, this is over here in librc data structures. And it's very simple, right? It's just an index vector from the row to a bit set of columns. I would probably have it start with an empty vector. And when you go to add to a given row, if the row doesn't already exist, it adds empty rows in between, like up to get to the point you need, essentially. just grow it as much as it has to. I think we even have a helper function for that on vector. And then like contains is very easy. You know, if the row doesn't exist, then it doesn't contain anything. And similarly, like you have to adjust some of this other logic, but not much really. Anyway, I guess iter, you might have to use like either or something for iter, but there's probably a way to finesse it. The problem being that the impl iterator is going to want one type. So usually if you have an if, it gets a little annoying. But you might be able to do it by like making it an optional something and flat mapping it or something like that. Anyway, so if we did that, and then we just don't need to have this argument, and the rest of it will just work, basically, as far as I can tell. Should just fall out from that. Then we can move this earlier, and then we can pass it into the, where was I? Here. If we create the values here, we pass it into type check, or maybe have type check create them. Either way, it doesn't really like. The point is they'll come back then as like part of these constraint sets or something, and we'll just give them to the region inference context when we create it, and it'll just move them right into place. And then there's no copying and all that stuff. It's just direct. That's the idea. Any questions?
No, that makes sense.
Okay. Yeah, it seems like it should be straightforward enough. The hardest part is modifying sparse matrix to not care how big things are. The only thing I would say then is the last little detail is right now we have this. Oh, yeah, you might or might not want to start from my PR, which not because it's kind of orthogonal. My PR being the one that computes SCCs. It's kind of orthogonal, but it touches this code. But the main thing is there is this code here, generate constraints. This code had the job of taking the liveness information from type check and translating it into this bit set form, right? Which is really pretty straightforward. It just iterated over the vector and added it to each. So all we would want to do is not do that, basically. Don't have to do it anymore. We might still want to like do the Polonius. This is the Polonius part. I don't know. We could probably move this logic into type check, or if we break Polonius for a little while, we can come back and fix it. I guess I don't know. That's the hardest. That's the other tricky bit, is figuring this part out. Okay. The thing that changes on my PR is perhaps relevant. There's one change. Right now, my PR still has the liveness set, just like this code does, no changes. But when we call add live point, all it does is add a bit into the set. Right here. I'm going to switch branches here. On my PR's branch, where is that PR? Oh. Well, this is my, I guess I don't have it checked out. Oh, hold on. Okay. So on that branch, where was I? Even infer mod. This is the corresponding function, add live element. It got renamed for reasons. It now adds it both to the liveness constraints, but also to this other set. So I'm not sure how much you saw that PR, but what it does is it finds cycles in the region inference graph, where you're saying like this region has to be bigger than that one, and then if there's a cycle, that means they all have to be equal, otherwise you can't satisfy that. And so it collapses those into one element, and it has a mapping from each region to the cycle that it participates in. And the nice thing about that is then you get like a DAG, so it makes it easier to do inference, and faster in particular. Not easier, I guess. The main thing is, so basically all we would want to do, if we had the liveness, or those cycles get computed right here. This is where we compute the cycles and make, and this is, so then we have like a second set of values here. If we were, if we had the liveness data already, we could just iterate through the liveness data, sort of go through each region, I mean, find the cycle that it's a part of, and add it to the value. It would be something like, I can put it somewhere else, but it would be something like, for each region R, let SCC is constraints SCC dot SCC this, so this kind of looks up the cycle that it's a part of, and then I don't know, I don't think we actually have the API call we would probably want, but you would sort of say SSC values dot merge into so you would say I guess we'd have to add some I don't think this API is there, but you want to take the bit matrix that corresponds to R and merge it into the bit matrix for this SCC. And you would just do that for every, they'll get union together basically, which is what we want. So, but I don't know, who knows when that PR will land. So maybe just do it and we'll rebase whichever one on top of it. But that's the only real interaction between them.
Okay.
Alrighty, I hope that was helpful. I will post this video. And I'll talk to you later.
Okay.